Therefore, mass m equal to k upon 2. If I take 12 LCM of 2, 3 and 4, what it will be? Then if I take 12 LCM, it will be 2 6 or 6 times. It will be 4 to the 8 minus 8. It will be 3 times. First let me write. It is k upon 2 into 12, 24. The outside are taken. Okay. But before integrating this, let me write here 0 to 3 limits. Still we are not integrating with respect to x. First let me summarize them. It will be 6 into x into a minus x whole 4. Okay. And minus sign because 4 to the 8, it is 8x into a minus x whole 4. Okay, plus sign. This is 3 times 3 into x into a minus x whole 4 upon total 12 or 24 are taken outside. Okay, so this 12 is already taken outside. This is only these 3 terms. This is sorry whole 4 into dx. Now, see here, this is 6 plus 3, 9. 9x into a minus x whole 4 is negative 8. It will be only one time. It will be k upon 24, 0 to a x into a minus x whole 4 into dx. Now it is to be integrated. Now if I take a minus x something, let me substitute a minus x something, theta or t, putting a minus s, okay, as, let me take capital S here, or capital T, or nothing else. Let me take t here. That would be okay. It is t here. Therefore, x equal to this x equal to, okay, so x will be a plus t. This is a plus t here. Okay, so let me put here a minus x is equal to 3. Therefore, x equal to x taken to that side will be a minus t is equal to x. If I integrate this with minus dx equal to dt, differentiating, okay, differentiating it with respect to t, let me take differentiating it with respect to t, we get this value minus dx or dx equal to minus dt. Now what is the limits here? If I put in place of x as a, it will be 0 to t equal to 0, and at 0 it is a to 0, but the negative sign is there, with positive again. It is k upon 24, a to 0 limits. Let me convert this whole into t. Now x is a minus t into t4, but this whole are taken as t into minus t. The limits are interchanged because of this negative sign. Let me change the limits, interchange the limits. For mass equal to k upon 24, limits now 0 to a. For this minus sign, I change the limits. So it is minus a to 0 to a. A minus t into t4, that means a into t4 minus t5 dt. Now let me integrate with respect to t here. Simple integration. Finally, what is the integration of this? T, I have converted this whole into t. Now integrating with respect to t, it will be k upon 24. Integration of this with respect to t, then limits are to substitute in place of t and a. It is a t5 upon 5 minus t6 upon 6, 0 to a here, limits, simple. Okay, this is k upon 24. If I put here t in place of t as a, a6 upon 5 minus this is a6 upon 6. a6 upon 6, a6 upon 5. It will be 6 5 the 30, 30 as the LCM here. It is 30 LCM. K upon 22 into 6 minus 5 into 1, 86 upon 30. Let's come out. It is KA6 upon 30 into 24. Very strange, it is this much. Because integration with respect to t, p5.5, oh sorry, 56 upon 6, that means this is a6 upon 5 minus a6. 6 minus 5, that means 1 upon 30. So that means k upon 30, 24, 3 72, 720. Okay, 720 in the denominator. So answer again. Question number 3rd. Mass of this is Ka6 upon 720 units. Maybe units here. Okay, so this is the value of question number 3 here. Final answer. Now let me take next question, 4th one. What is question number 4? Let me check. Okay, now question number 4. What does it say? Question number 4. A plane lamina, okay, in the form of a quadrant of the ellipse, in which density at any point varies as the product of the coordinates of that point. Okay, and the mass. So this question is, I think, similar to the first question, because that was also ellipse, but only the wordings are different. Because these questions are given by two students online differently, but the question I think is similar. Let us solve it now. What is given here? 4th question. Here we are given an ellipse. We are given here an ellipse. X square upon a square plus y square upon b square equal to 1. It says a lamina, plane lamina in the form of a quadrant of an ellipse. Okay, same quadrant of an ellipse is that this is b height, this is a. So here it is again. Okay, this is straight parallel to the axis of y. This is b here. Y equal to b, that means 0 and b. This point, at this point, this is a and 0. 0 0 here, origin O here. Okay, x axis, this is y axis, y dash, and x dash axis. Now here y equal to 0 on the axis of x. Here y equal to this one. Y get final y square upon b square equal to 1 minus, that means b upon a square 1. A square minus, let me write a square minus x square, or we could write dash equal to b into square root 1 minus x square upon b square. That is also can be written. That can also be written like this one. Then a square, if I take LCM inside the square root, after that a will come out. Either this or this. The y here at this point. This is parallel to the. Now if I draw a parallel line to axis of x, and what is the limits of this variable? Here x equal to 0, here x equal to a. These are the limits for x variable. Now let me solve it. But limit is given for density. What is the density given to us? Now density, it says that in which the density at any point varies as the product of the coordinates of that point. Coordinate of that point is x and y here. So rho equal to, let me take here density rho at point xy, the point xy is equal to, it says k into x into y. Now it varies, it is proportional, let me write here, is proportional to xy. Therefore, or equal to rho equal to kxy. K is a constant of proportion. K is a constant of proportionality, constant of proportionality, proportionality, sorry, constant of proportionality. Okay, constant of proportionality. This is value of rho, and the limits are for x variable, limits are 0 to a, and y variable 0 to h. So let me find the total mass. Therefore total mass of the elliptical quadrant here is given by, I think this question is done in the question number 1. Only wordings are different, but they are similar type of question. Limits are 0 to a for x coordinate, 0 to b upon a under root a square minus x square. Okay, for y coordinate, here rho into dx dy only. That means this is equal to 0 to a, okay, 0 to b upon a square root a square minus x square into rho is k x by into ds dy. This is total mass here. Now let me integrate this. The integration of this will be, let me write here. So m total mass is equal to 0 to a, the first limit of x variable, and the limits of y variable are this. So let me integrate this with respect to a constant are taken outside. This is x. This is the constant for y variable. First we have to integrate with respect to y. The limits are in terms of x variable. We have to integrate this with respect to y first. Let me write it as x into, okay, let me write this 0 to b upon a square root a square minus x square into y into dy. This I have to integrate with respect to y first. First, with respect to y, integration will be this much. Y square upon 2 here with k 0 to a x into y square upon 2. Limits are 0 to b upon a and a square minus x square into b. Absolutely limits here k equal to a x into limits of y is y square to be b square upon a square, only a square minus x square, square is going to be considered upon 2. Let me take this to outside, this is k upon 2 here. Okay, so x into b square upon a square, only upper limit will be substituted in place of y square. In place of y square, that means this square will cancel out. This will be b square a square, b square and a square, this square and square into this. First let me multiply this by x and b square from a square, let me take outside. K into b square a square upon 2. Limits 0 to a x into this, that is a square into x minus x cubed, so x square into x into dx. Now let me integrate this. Further integration of this will give us mass m equal to 0 to, first let me write the constant value. This is k into b square a square upon 2, and integrate of this 0 to a limits will be substituted, but x integrated as x square upon 2, x is integrated as minus x cube is integrated as x whole upon 4. Limits 0 to a only. Now x limits are here. Okay, now let me substitute the x limits. So in place of x we have to substitute a here. So this will be k into a square b square upon 2 into, this is a4, I'm sorry, What is a square are taken in the numerator? This was in the denominator. This was b square upon a square that are taken here. B square upon a square. A square will come in the denominator. This is a4 upon 2. Because in place of x, if I substitute a, b a square into a square is a4. This is a4 upon 4. Now we can solve it. Because this was upper limit was b upon a in case of y. B square upon a square will come in the denominator here also after substituting the limits. So that was here. So it is a4 upon 4. 4 is LCM. Twice a4 minus a4, that means a4 upon 4, which is a into b square upon twice into a square into a4 upon 4. A square and into b square. The answer is a upon 8. Go to the 8. A square into b square. This is a square only. Now, the same answer I think was obtained in question number 1. Same questions are given. They are clearly given that rho equal to pxy, but in wordings it is given, and with the density at any point varies as the product of the coordinates of that point of the final mass. That's the question here. Let me talk about questions. This is answer here. A square b square divided by 8. That's the answer. Now question number 5. Let me talk about with the question number 3. Now let me check it. Question number 51. Find the mass of a plate in the form of a loop of the lemniscate. Okay. Lemniscate of Bernoulli. Bernoulli is r square equal to a square, or that was given by Bernoulli. So this is the figure I'll just talk about. The density at any point varies as the square of the distance of the point from the pole. Okay, it means polar coordinates are the pole given to us. So let me write here. Question number 4 is given to us. So given here. The Bernoulli r square equal to a square into cos 2 theta. Okay. Now density rho varies as k into lambda into, let me take r square, maybe k or lambda, doesn't matter. So here, the density at any point varies as the square of the distance of the point from the pole. So let me take this point is r in the pole, r rho equal to, and the density rho, this is density rho, okay, is equal to lambda times or k times, let me take this is r, k into r square, where k is a constant of proportionality. Now rho varies, density varies as the square of that point on the circumference of this orbital. Okay, and the mass of a plate in the form of a loop of the lemniscate of Bernoulli is the density at any point varies as the square of the distance of the point from the pole. From the pole, the distance of that point, let me take it r square, this is r here. Okay. This is rho equal to kr square. These two things are given to us. I want the figure here. Let me talk about solution. So, for the Bernoulli's figure, I mean this figure of this is the lemniscate of this figure. This is a question number. Let me check whether the mistake is given or not. Okay. So, for the lemniscate of this point, now lemniscate of this point is given to us as, okay, so in this case the lemniscate of this Bernoulli is just like this figure. Okay, now this is making a 45 degree angle, so also making a 45 degree angle, and this is the pole in between. This is x axis, this is y axis. Okay, now if I take polar coordinates of this, let me take this line by straight. Here it is P point. The distance of this P point. Now here theta is equal to that theta varies from minus pi by plus pi by 2. Theta is equal to minus pi by 4. Sorry. To here theta is pi by 4. Theta is equal to plus pi by 4. Pi by 4 to minus pi by 4 to plus pi by 4. The limits of theta here. And r varies from this point to this point. Here it is r equal to that value. So r is equal to 0 here at this point. So r equal to 0 to this r. R is square root of this. R is equal to square root of that means a under root cos 2 theta. Okay, so r is equal to 0 to r is equal to a cos 2 theta. This value. So r, this is Leibniz gate here. For this Bernoulli is the figure is of this kind of shape. Okay, this is plate given and the mass of the plate in the form of a loop of the Leibniz gate of Bernoulli. R square equal to a square cos 2 theta. The density of the point varies at the square of the distance of the point from the. Okay. So if I take this as a pole, from this pole this distance is r here. This point P r theta, let me take. At point P, coordinates are r theta, and this is d theta here. This is theta here. Theta varies from here. Theta is not 5. This is the the line which is known as, this is pole point here. This is linear line or straight line, okay, linear axis in this case, or polar axis in this case. So in case of polar coordinates, we have to discuss about this point. P r theta is any point P with having coordinates r and theta. At this point, the distance of this point is r from any pole. It is given pole. The square of this r is square. K r square is the value of pole. Now let me find the mass of this. So elementary mass first. If we find out what is elementary mass, here the elementary mass is equal to rho into dx dy. But if I take rho in polar coordinates, it will be rho into r d theta dr. Okay, so this is r d theta dr, rho into r d theta dr, elementary. This is in case of partial coordinates, in polar coordinates. R is Jacobian. We always find out the Jacobian gives us when we change the variables, one variable to another variable, which I have discussed in the previous lecture. This R is Jacobian variable. Okay, so del x del y del z. In this case del x del y. So del x by oblique del theta del r. If I find out del r theta with respect to r and theta, then the value will be r of Jacobian. So this is that is Jacobian r. This whole dx dr dy will be converted to r d theta dr. The rho is kr square. This is elementary. So therefore, the value of the mass of this Leibniz gate. Therefore, mass of the complete mass or total mass of the Leibniz gate. The plate here. The plate is in the form of a loop of the Leibniz gate of the plate. The mass of the plate in this case. Here is mass of a plate in the form of a loop of the Leibniz gate. Okay, mass of the Leibniz gate plate or plate loop of the plate. Okay, will be equal to, let me say m here, mass is given by double integration sign. Here theta is minus pi by 4 to plus pi to try to understand, and r is 0 to a under root cos 2 theta. This is the rho into r d theta dr. But here rho value is how to be substitute. That is minus pi 4 plus pi 4. Here second integral is 0 to a under root cos 2 theta. Here it is rho. Value of rho is k times r square into r into d theta dr. Now this is r cube here. Integration of r cube, that will do So that's okay. And this limit minus pi 4 to plus pi 4 can be converted by definite integral properties. Property of definite integral minus a to plus a, it is twice 0 to a. That means it will be twice 0 to pi by 4 limits. This is one of the property of definite integrals. When limits are minus a to plus a, it can be written as twice 0 to a. Okay, that is one of the properties. So these are converted into 0 to pi 4. K is the constant are taken outside this K. Okay, now second integral sorry, limits are 0 to a cos theta inside the square root. Okay, this is r cube into dr, r square into r is r cube into dr whole d theta. Okay, now let me integrate this to r cube. So answer will be, I mean mass will be, for total mass is equal to twice k 0 to pi by 4. Here it is integration r cube r4 upon 4. So limits are 0 to a cos 2 theta square root of a. Okay, into d theta now. So r4 upon 4. Okay, so let me solve it. So integration of this will be, okay, so integration of this is given as twice k constant as it is. In place of r4 of 4, let me take this 4 outside. It is 1.20. This 4 are taken outside. Now in place of r4, I have to substitute this. It means a4 integration sin 0 to pi by 4. 0 to pi by 4. Pi by 4. a4 into cos 2 theta whole square. So this is 4 upon 2, that is 2 twice power of cos square theta. Let me write here square of square 2 theta divided into this. Now let me first convert this cos 2 theta into angles. Further, this is k upon 2 outside, 0 to a4 also let me take outside. a4 k a4 outside, 0 to pi a4 is cos square 2 theta. It is nothing but 1 plus cos 4 theta upon 2. 1 plus cos 4 theta upon 2 into d theta. Since we know this, cos 2 theta is equal to 2 cos square theta minus 1, or 1 plus cos 2 theta equal to 2 cos square theta. No, 2 cos square theta. So 2 are divided here, cos 2 theta. Cos theta will be 1 plus cos 2 theta upon 2. Cos twice theta, cos square 2 theta will be equal to 1 plus cos 4 theta upon 2. Upon 2. This is 1 plus cos 4 theta upon 2. This implies that cos square theta is equal to 1 plus cos theta upon 2. If angle is single, then it is twice. When it is twice, then it will be 4 times. It is cos 4 theta. Since this value is formula, this is trigonometric identity. From that we have taken this formula. Now, or if I change the limit, okay, I could change the limits also. No problem. That could also be done. If I change 2 theta equal to something, then it will be positive. That can also be done. Okay, without changing this in trigonometric identity, I could do this also. Pi for root pi. So that is cos square theta then 0 to pi by 2. Okay, then that can also be done. Okay, now let me do this in this way. With the answer, let me find out from here. It can be integrated now, or it could be done by changing twice theta, the angle, putting t and pi by 4 angle, limits will be 0 to there. Pi by 2, and this will be cos square t of cos theta. Then that can be integrated. This is now even over here. It will be pi by 2 into only pi by 2 here. Only pi by 2 of this answer. So this value whole will come out with pi by 2. Let me check what is the answer of this question. So finally, let me write here. Therefore, m is equal to KA4 upon 2. This 2 also has come out. It will be 4 here. Let me write 4. The integration of this one integration is theta plus it is sine 4 theta upon 4. Limits are 0 pi by 4. Okay, in both the cases, this theta will be pi by 4 here. Only pi by 4. This will be 0 because if I substitute here theta is pi by 4 first, then it is sine pi is 0 and sine 0 is 0. In both the cases of this limit, sine 4 theta, cos theta is sine 4 theta upon 4 positive integration. Sine 4 theta upon 4, if I substitute limits here, pi by 4, it will be 0 in both the cases. Pi at pi by 4 theta, if I put 4 into pi by 4, this is 4 cancel pi, sine pi is 0. Sine pi is 0, sine 0 is also 0. In both the limits, this will be 0, but it is there. It is KA4 upon 4 into pi upon 4. It is KA4 upon, that was 1.2 into pi by 2. So that was, it is pi by 4 here. Okay, 1.2, because that will be done by Wallis formula also. Changing the limits to theta equal to t, the limits will be 0 to pi by 2 and cos square theta of integration of by Wallis formula will be 1.2 into pi by 2, that will be pi by 4 here. Because this is KA4 upon 16. The answer here, final answer is the mass of this plate, this lemniscate plate or plate of the this Bernoulli's lemniscate will be this much. This is the answer here. KA4 upon 16 is the answer of question number 5 here. Question number 5 we have done. So let me talk about question number 6. What is question number 6 say? Let me check it. Question number 6. Okay, now it says a wire is in the form of a cardioid. Okay, what is given to us? Now here it is a curve for a wire symbol. Given here is a cardioid. Sorry, a wire, a cardioid form. That means R is equal to A into 2 into 6.